Here is a kinematics problem. Superman is standing in the window of a building 40 meters above the street. A baby hurtles past, having been dropped from a window 15 meters higher. With what acceleration must Superman descend to catch the baby just before it is too late? Assume Superman steps out of his window the very instant the baby passes the window. Okay, let's draw our scenario. So, here is our building, all right? And our baby, let's say, is right here. And Superman, let's say, is right there. Now, Superman is at 40 meters. And the baby is dropped from a window 15 meters higher, which means that the baby is at 55 meters before the baby's dropped, right? This is like the very first scenario, like before everything happens, right? So baby is at 55, Superman is at 40. Now, let's write out all the kinematics variables. So, our initial position for the baby is 55 meters, but since the baby's being dropped, and the baby will eventually reach somewhere close to the ground, the final position of the baby is going to be 0, right? So change in x equals 0 minus 55, right? Final minus initial, which is just negative 55 meters. Okay, since it's being dropped, the initial velocity is 0, and again, since it's being dropped, the acceleration on Earth is negative 9.8 meters per second squared. Okay, and the time for the baby, we don't know how much, so we're just gonna leave it as time for baby, TB. Okay, now for Superman, the change in x for Superman is gonna be negative 40. Initial velocity for Superman is also 0. Acceleration, we have to figure it out. And then time for Superman is just TS. Okay. Now, the problem says that the Superman steps out of his window the very instant the baby passes the window. So let's figure out the time for this distance. Okay. The time the baby goes from 55 meters to 40 meters, which means that change in x in that scenario is going to be negative 15. Okay. Initial velocity is still 0, acceleration negative 9.8. Okay. And time is what we're supposed to figure out. So our kinematics formula, change in x equals VOT plus half AT squared, negative 15 equals, initial velocity is 0, so this entire thing is basically 0. So we're left with half A and then T squared. Okay, so time is 1.7496 seconds. This is the time for this distance for the baby, okay? Now, we know that Superman is going to travel for this much time less than the baby, because the Superman starts off when the baby gets to 40 meters. It says he steps out the very instant the baby passes the window. So the baby has already traveled for 1.7496 seconds when the Superman starts out. So, therefore, the time for Superman is going to be the time for baby minus 1.7496. Because Superman is just going to travel for this much less. Okay? The time for both of them is not going to be the same. because the baby has already started moving, and the baby has already moved 15 meters when the Superman starts out. Okay? Now, let's figure out the time for the baby for 55 meters. Okay? Now, this would be change in x equals negative 55, initial velocity, 0, acceleration, negative 9.8, and then time for baby. We're going to use the same formula. Again, this thing is going to cancel out because initial velocity is 0. Okay. Now, the time for a baby is 3.35029 seconds. Let's just make that 3.35 for simplicity. So, time for baby, 3.35. Now we can also solve for Superman's time, because we already have an equation for Superman's time in terms of baby's time. Therefore, Superman's time equals 3.35 minus 1.7496, which gives us 1.60066 seconds. Okay, now we have the change in x for Superman, initial velocity, and time. Since we have our 3 kinematics variables, we can now solve for acceleration. And guess what? We're using the same formula. Change in x equals VOT plus half AT squared. Change in x for Superman, negative 40. Initial velocity, 0, so this thing cancels out. 1/2 acceleration, and then time. Okay. Which gives us acceleration as 31.2241 meters per second squared. So, in order for the Superman to catch the baby, the Superman is going to have to accelerate for 31.2241 meters per second squared. This is your final answer.